Okay. Good morning, everyone. The topic of my today's presentation is on Isabelle HOL Formalization of Semi-Thue and Conditional Semi-Thue systems. Here are the contents. Basically, I formalized the Semi-Thue systems and conditional Semi-Thue systems and their related result. And I also introduced some new result about Semi-Thue and conditional Semi-Thue systems. Semi-Thue systems, it is generally accepted that Axel Thue is a Norwegian mathematician. First introduced Semi-Thue systems, also known as string rewriting systems, in order to solve the word problem of semigroups and monoid. The word problem of semigroups and monoid and the groups are one of the fundamental problems in the semigroups and monoid and groups. Semi-Thue system is basically of a finite alphabet is a set of ordered pairs. And we have if U rewrites to V, if there is a match in the U in the rewrite systems. For example, AB, there is a match in the left-hand side, AB. Then AB can be rewritten to BA, so BA here. And also the AA, if there is a match in the left-hand side, then it can be rewritten to A. So here, BAA. So AA can be matched, and it can be rewritten to be AB here. Thue congruence induced by R is the relation. This is a symmetric, reflexive, and transitive closure of the rewrite relation R. So in the above example, ABAB and BBA are convertible using this rewrite system, Semi-Thue system R. So basically, the Semi-Thue systems, if there is a match in the left-hand side, we can just rewrite to the right-hand side of the rule. Thue congruence is the equivalent word with respect to R. So if W is a set of equivalent word with respect to R, is the congruence class of WR here. In the above example, ABABR, the congruence class of ABABR is this one, ABAB, BAAB, BAB, BBA, and so on. Monoids are fundamental algebraic structures widely used in mathematics and computer science. And monoid is a set equipped with associative binary operations and a two-sided identity element. So sigma star is a monoid called the free monoid. The sigma star is a monoid without any relation. The elements are all finite strings from sigma, and operations are string concatenations. And the identity is the empty string. But if we add some relations, and the relation equation can be also converted to the rewrite system R. If we use some ordering, for example, length lexicographic orderings. And if we have introduce some relation in the monoid, we can consider the vector monoid. So the element of the vector monoid here is the congruence classes, and the operation is a binary operation such that this satisfies this equality here. And the identity is the congruence class of the empty string. So given a Semi-Thue system R over monoid M is finitely presented by sigma R. If M is this quotient monoid, vector monoid MR, and both sigma and R are finite. So if we don't have any relation, is a free monoid. But if we have some equations, and this equation can be converted to the rewrite system, Semi-Thue system R, then we have a finitely presented monoid. So the word problem of the monoid is following decision problems, given two words, UV, decide UV in M. So different strings in the these sigma stars can be the same element up to the equivalence, congruence. So we have to decide whether we can decide, we need to decide if U equals V, two different strings can be the same element in M, the finitely presented monoid or vector monoid M. But the word problem of finitely presented monoid is undecidable in general. So we need some specific, we need to consider some specific restrictions. If R is confluent and terminating, then it is decidable. So confluent and terminating is the confluent is the if a string can be rewritten to two different strings using the realized stems, it can be joined. It is joined if it's confluent. And terminating is there is no infinite chain of realized stems using R. Group is a monoid in which every element is invertible. More specifically, monoid is a group if for all U in the alphabet, there is some V such that UV, this is invertible. VU is invertible. So the purpose of completion of monoid, monoid is presented by a finite terminating semi-Thue system, but it is not confluent. Then one may attempt to construct a finite complete semi-Thue system equivalent to R using completion procedure. So if we, the purpose is that we want to construct a finite complete semi-Thue systems to solve the word problems. But if we have some monoid presentation, and even though if we orient the equation into Rewrite systems using some terminating Rewrite systems, using the length lexicographic ordering or something other ordering, but it may not be complete confluent. So if we can construct a confluent Rewrite semi-Thue systems, then we can have a decision procedure for the word problem in monoid or semi-groups. It is known that an STS semi-Thue system on sigma point can be associated, sigma star can be associated with term rewriting systems. So previously we have some semi-Thue systems, but it can convert it to the term rewriting system and vice versa, because term rewriting system is also well established research. It already have a well established research. So if we can, for the semi-Thue systems, we can also convert to the term rewriting systems. So the Knuth-Bendix algorithm for semi-Thue systems are already known in the literature. And there are also known inference systems for the completion of term rewriting systems. But the algorithms approach for the Knuth-Bendix algorithm, Knuth-Bendix algorithm is an attempt to construct a complete rewriting systems. So Knuth-Bendix algorithm for STX is already known in the literature, and there are also inference system-based completion of the term rewriting systems. The proposed approach is an inference system for completion of semi-Thue systems instead of using the algorithms, Knuth-Bendix algorithms. The advantage of using this proposed approach is a simple linear time string matching and length lexicographic order instead of using unification and more complex term orderings. If we use the abstract completion for completion of term rewriting systems, it is not tailored towards the completion of semi-Thue systems. So we have to use some ordering for the terms and conversion, this conversion, but this is not straightforward because in the proposed approach, we can just use simple linear string matching and length lexicographic orderings. So the inference system for the completion of semi-Thue systems, for the proposed completion of semi-Thue systems, E is basically a set of equations or critical pairs that is going to be oriented using the length lexicographic ordering. Short lex order is a length lexicographic ordering. And here, the left-hand side cannot be the empty strings because the empty string is the length is the minimal. So left-hand side cannot be the empty. So the inference system, advantage of inference system is we can use the modular approach instead of using the algorithms. So deduce, if we have this is premises, and the upper part of the is premises, and the lower part is conclusion. If the condition is satisfied, the conclusion is derived. And basically, if we have a overlap U2 and there is an overlap between the two rewrite rules, and there is overlap, we just resolve these overlaps by adding the equations. Simplify is we just using the simplification by rewrite rules U2 to T. And orient is here, the S equals T is in the equational part. R is a set of rewrite rules. Here, S equals T can be oriented into rewrite rules using this one. So as you can see, the equation is the bidirectional, but the rewrite rule is directed equations. So it's better to use rewrite rules instead of keeping the equations. Collapse is also applying the rewrite rules using U2 to T. And compose is, we have also rewrite U to T to this one. So this is more easier to apply simplifications. And delete is, this one is a trivial one, so we can just delete this one. S equals S. So fair non-failing run is, if we have this one is applying the inference rules, SR is applying the inference rules, can be obtained from the ER, and E prime R is the resulted application of the inference rules. And run is we start with a set of equations and the empty rewrite systems. But when you do the runs, we just move to the equations into the oriented rewrite rules and consider the overlaps. And if it fails, means that there is an equation in the set of equations. The purpose is to find the complete rewrite system Rn. So if the equational part should be empty, and if it's not empty, it fails. The pair is basically considered, CP is a critical pair, considered all the critical pairs. And the correctness of the proposed inference system is that for every pair non-failing runs, Rn is a complete semi-Thue system for an initial final set of equations, E equals EO on sigma point, sigma star. Now, the second part is the conditional semi-Thue systems. Conditional semi-Thue systems, we have a condition in the semi-Thue systems, and a finite presented monoid with a decidable word problem may not admit a finite complete presentations. For example, this inference rules, the inference system, the input of the inference system does not terminate and it can go forever. So in this case, it does not admit a finite complete presentation because it's not finite, but it may admit a finite complete conditional presentations. For example, the monoid with this one, if we apply the inference system or Knut-Bendis completion procedure, the monoid is, it does not admit an equivalent monoid presentation, but if we have a conditional semi-Thue systems, it has a finite presentations. The type of conditional semi-Thue systems is depending on the string rewriting relations induced by the conditional semi-Thue systems and how conditions are evaluated in the conditional part of the conditional string rewrite rules. So it can be, there are three different types of the conditional semi-Thue systems. First one is the left-right join CSTS, and we derive the rewrite relations from the conditional semi-Thue systems. In this case, we can use the left and right context UV for evaluating the Rn in the conditions. Instead of just evaluating the condition only, we can use the context UV with the help of context of UV, and we evaluate the conditions. And if we satisfy this one, we can add the rules. Right join is, we just use the right context B here. And the pure join is there is no additional context to evaluate the conditions. So pure join is the most restricted case. And as you see, the C goes to D with the condition A equals B. A equals B cannot be satisfied. But if we use the right context, ALBL here, it can be joined, ALBL. So now CL-DL can be the rewritten using the CL can be written DL using the right join rewrite steps. Left-right join is the least restrictive, and we can use the context and both of these CL, DL, and the LCM and LDM hold. Reductive CSTS is if the rewrite rules have this left-hand side is bigger than the right-hand side, and left-hand side is bigger than all the conditional part, is reductive. And the good thing about the reductive conditional semi-Thue systems is that if it's a finite reductive and right join, then this one is terminating and also decidable. Also, if R is a finite reductive right join CSTS, then RP pure join rewrite step is also terminating and decidable. So the limitation of the left-right join conditional semi-Thue systems is that non-overlap may not be joinable for left-right join CSTS. So if non-overlap can be joinable, then we can just use the critical pair, only considering the critical pair. But if non-overlap may not joinable, the confluence criteria is more involving and it's difficult to handle. Check. So the example is that if we have this one is non-overlap because the B is related to U using these rules. Using these rules, and C is related to D, so different positions and different rewrite steps, and then but this one is not joinable. So this is the limitation of left-right join CSTS. So critical pair for right join and the pure join CSTS, if we consider the critical pair, or critical pair arises when there is an overlap. And if there is an overlap between two rules, as you can see, UOY and XUOY, there is overlap here. And if there is an overlap, critical pair can be obtained. In these times, we have to add conditions, append the conditions. Here we have a Y here, so we also have to append the conditions here. And this time also the Y is appended here. So we also have to append these conditions with conditions. And the pure join has the critical pair is simpler, and we don't have some additional context here for the overlap. So the joinability of critical pairs is that if it's right join CSTS R, a critical pair is joinable if there is a SIY and the TIY, the conditions is evaluated true, and then the SOY, TOY is evaluated true. For the pure join is that for the conditions are joinable, then the SOY and TOY are joinable. So joinability of critical pairs is used for the confluence criteria. So R be a finite reductive right join, then the R right. So right join is confluent, right join step is confluent if and only if all critical pairs are joinable with respect to right join steps relations. So confluence criteria for right join and pure join can be established using the critical pair, joinability of critical pairs. Inference rules for conditional equation series, inference rules can be so conditional equation theory is that we can derive the equivalence using the conditional semi-Thue systems, and this equivalence S equals T, and the reflex symmetry, transitivity, and congruence. And the replacement rule can be one of the replacement rule can be selected. And if S equals T is equivalent with respect to left-right conditional equation theory, if it's derived consistent of reflexive, symmetry, transitive, congruence, and replacement rules. And right join semi-conditional semi-Thue equation theory, conditional equation theory is derived if it's reflex symmetry, transitive, congruence, and the replacement R rules. Similarly to the pure conditional equation theories. The related result is that if it's T1 and T2 is equivalent with respect to the LR conditional equation theories, then it is convertible using the left-right joint semi-equational steps. And if it's confluent, then the left-right semi-Thue realized steps is the same as the left-right joint steps. So the semi-equational one is the bidirectional, but the joint one is the directional. So it is more simpler. So we can monoid, it can be defined similarly using the previous Semi-Thue systems. And the decision procedure, in this time, you can just use the, instead of the Semi-Thue system, you can use the conditional Semi-Thue systems using the congruence relations. So in the Isabelle, we just use the inductively defined predicate in the Isabelle holes. And for the E is basically unordered pairs, but for the technical convenience, just use the ordered pairs. And right join realized steps can be used using the this inductively. C is a context. String context. Context for string is based on the existing formalization of context for terms in Isabelle. So it's the formalization is built on the Isabelle and the existing formalization of a monoid. And the right join conditional Semi-Thue systems also using the locale and the assumption locale conditional right join Semi-Thue system represent the this one. So S is the denotes the alphabet. So using the existing locale monoid. And summary is that I presented and formalized the inference system for the completion procedure of Semi-Thue systems, which is adapted from the existing Knudsen-Bendix completion procedure of Semi-Thue systems, and an abstract completion procedure of term rewriting systems. So the advantage is the simple and efficient string matching algorithm, and the inference system is more modular and easy to apply the simplification rules. And presented the formalization of a conditional Semi-Thue system and provide a new formalized proof of confluence criterion for right join and pure join Semi-Thue systems. And also provided a new formalized decision procedure for the odd problem of monoids presented by a finite complete reductive right join and pure join conditional Semi-Thue systems. Thank you.